All right, in case you are confused, this is not Vanilla Ice. This is the song Under Pressure by Queen. And we're going to be talking a little bit about extrinsic regulation of blood flow. So in order that we can better appreciate this, let's talk about extrinsic regulation of blood flow. Now it occurs, via input from the autonomic nervous system as well as from hormones. Now, we talked about intrinsic regulation, right? Intrinsic regulation of blood flow occurs without input from autonomic nervous system or hormones. Okay, so now we're going to talk about extrinsic regulation mechanisms. In the autonomic nervous system, we're going to specifically talk about the sympathetic division. It innervates arterial smooth muscle everywhere. And we're going to learn that the sympathetic division regulates mean arterial pressure via regulation of total peripheral resistance. So when I say total peripheral resistance, what the heck am I talking about? All right, well, let's take a look at this for a minute. Remember these two numbers? The average diameter of arteries, 4 millimeters. The average diameter of arterioles is about 30 micrometers. And now let's look at our little artery and arterial model. So the average artery diameter much larger than the average arteriolar diameter, to about a factor of 100. So when we see this 100-fold decrease in diameter between arteries and arterioles, we ask that question, what effect does this have on flow? Well, remember, from the Poiseuille's law, a reduction in diameter or radius is going to reduce the flow to the power of 4, or r to the 4th power. So what's this look like? Well, another piece of data that we talked about in lecture was that arterioles are the primary resistance vessels. This is a result of this difference in diameter between the vessels, the arteries, as well as the arterioles. So what does this look like? If I increase the arteriolar diameter from 30 micrometers to 40 micrometers, I'm going to reduce the resistance to flow into the arterioles. And if I do that, I'm going to reduce total peripheral resistance. Okay. Let's take the other direction. It's also true. If I were to reduce the diameter of the arterioles, this would increase resistance to flow of blood from the arteries into the arterioles, resulting in an increase in total peripheral resistance. So, when I'm talking about total peripheral resistance here, I'm talking about a global change, not a local change. When we talked about intrinsic mechanisms that regulate blood flow, that was regulation of blood flow on the local level to those local tissues. So let's recall that equation. Flow equals P2 minus P1 over the resistance. All right, and we talked about changes in local flow. But now, when we're going to start talking about global changes in flow, all right, throughout the system, throughout the entire circulatory system. So instead of referencing flow and referring to that as F, we're now going to talk about cardiac output. And instead of referencing to a pressure gradient as P2 minus P1, we're going to talk about the blood pressure gradient throughout the entire circulatory system, which is equal to the mean arterial pressure. And instead of talking about resistance at the local level, we're going to talk about resistance throughout the entire circulatory system, and that is total peripheral resistance. So, cardiac output, a little review. What's it equal to? Heart rate times stroke volume. Mean arterial pressure. How do we calculate that? 1/3 of pulse pressure plus the diastolic blood pressure. What about total peripheral resistance? We don't have a calculation for that, but we can say total peripheral resistance is the result of the overall level of dilation or overall level net constriction of all the arterioles within the system. So we're going to use these three values: cardiac output, mean arterial pressure, and total peripheral resistance, and we're going to plug them into that equation for flow that we've been using so far. And what we get is that cardiac output equals mean arterial flow over total peripheral resistance. Yo. And then if we do a little more rearranging, we come up with the equation that mean arterial pressure, not only does it equal 1/3 pulse pressure plus diastolic blood pressure, but now it also equals cardiac output times total peripheral resistance. So if I increase either of these variables, cardiac output or total peripheral resistance, I'm going to increase mean arterial pressure. So why do we need to modify flow in the global level? It's to maintain steady mean arterial pressure in the presence of changing cardiac output. Remember our boy, Clint Malarchuk? Yeah, that's this guy, the hockey player. Remember him? There's the blood on the ice. Blood pouring out of his neck. And one of the conclusions we drew from lecture was that this is going to reduce blood volume. Okay, let's watch how this works now. If I reduce blood volume, I'm going to end up then reducing stroke volume, right? I've got less blood in my heart every time it beats. Now we just said that cardiac output is the product of heart rate and stroke volume. So then, if I reduce stroke volume, I'm going to reduce cardiac output. And now cardiac output is directly related to mean arterial pressure. So if I reduce cardiac output, that means I am consequently going to drop mean arterial pressure. So then, if I drop mean arterial pressure as a result of a drop in cardiac output, well, this system, it needs to return mean arterial pressure back to homeostasis. Because if you don't have enough pressure in the arteries, the blood is not going to continue flowing through the arterioles, and there will then be no blood reaching the capillaries, no exchange of oxygen. You will be dead. Okay. So we want to try to modify that using this equation. We could either increase cardiac output or we could increase total peripheral resistance. This is the end of the system that we're going to work on with the next video. But I want to conclude here. Globally speaking then, if I increase sympathetic tone, since it's going to activate, it's going to result in the constriction of arterioles throughout the cardiovascular system, this is going to increase TPR, total peripheral resistance, in a global way, resulting in an increase in mean arterial pressure that would then be a corrective to a drop in pressure due to a drop in cardiac output. See how that works? And in the system, the next video, we're going to focus on the two primary mechanisms either increasing the release of norepinephrine or activating the adrenal medulla. Norepinephrine is released by postganglionic neurons of the sympathetic division of the autonomic nervous system. And remember that the adrenal medulla, when it's activated, that releases epinephrine, a mixture of epinephrine and norepinephrine into the bloodstream. It's going to be all throughout the cardiovascular system. And with that, this video is concluded. We'll pick up with that one. We'll pick up right here on the next video. See you again.